Greetings everyone, and welcome to our third section in Chapter 2. Today we're going to be talking about the idea of freely falling bodies. What happens when something actually falls? We want to look at its motion. We want to look at what happens with different types of motion. So, you want to keep in mind two questions as we move through our discussion here. First of all, what type of motion does a falling object exhibit? We've talked about the idea of something moving with a constant velocity. We've talked about the idea of acceleration. We want to be able to fit falling motion into one of those two categories. So we'll take a look at that. The other thing we want to look at is how does falling motion apply to when we have a ball released from rest? So if we just take a ball and drop it. What happens if we actually throw the ball downward? And what happens when we throw the ball upward? So keep those two questions in mind as we move through here, and we'll review at the end what we need to get out of this. So, the first thing we want to look at is, let's say we just have a ball, and we're going to hold it above the ground at rest, and we let go. We know the ball is going to fall. That goes back to any experience we've had throughout our life. The question is, what type of motion does this represent? Well, if you think through it, we know that we're holding the ball at rest, we let go, and it speeds up. It's going to speed up toward the ground, and it falls. So that tells us then that the type of motion that falling exhibits is an accelerated motion. It has to accelerate. If it did not accelerate, when we let go of the ball, it would just stay there at rest. It would just kind of float in midair, and we'd be confused as all get out. Why is that floating there? It has to accelerate. If we know it accelerates because it speeds up from rest, so we can say it's accelerated motion. And we can actually additionally say it's accelerating in the downward direction. It's accelerating toward the earth. So we're going to say downward, but what we mean by that is it's accelerating towards the Earth's surface. It's toward the center of the Earth. So with that in mind, we want to introduce this idea of what's called free fall. When we talk about falling objects in class, we're going to refer to objects in free fall because we're going to make a couple assumptions about the motion of those freely falling objects. And there's mainly three assumptions we make. First of all, freely falling objects do not experience any air resistance. And we're going to talk more about that assumption here in a little bit. And the second assumption we're going to make is that freely falling objects are only under the influence of gravity. You've all heard the term gravity before. It's something we'll be revisiting later on in class. But the idea is that when an object is in free fall, gravity is the only force that's actually acting on the object. It's pulling the object toward the Earth. So that's our second assumption. And the third assumption is then that all freely falling objects accelerate at the same rate, and that rate is what we call the acceleration of gravity. Now, with the acceleration of gravity, we actually have a value for it, and we can verify this through various experimental procedures. And the value is, we found, that when an object is in free fall, objects will accelerate at the Earth's surface at about 9.8 meters per second squared in the downward direction. This is an acceleration. We said accelerations have a size and direction. The size is 9.8 meters per second squared. The direction is downward. So when things fall, they fall toward the Earth, and if they're in free fall, they're going to accelerate at 9.8 meters per second squared downward. So with that in mind, again, the key point here is it has to be in what are called free fall conditions. So one of the key assumptions of that is air resistance. Why do we ignore air resistance? Well, think about this. If we just did a simple little experiment. Let's say you have the textbook. You also have a sheet of paper. You hold both up in the air at the same height. They both start at rest. You let go. What's going to hit the ground first? What's going to fall first? Well, you should be able to just identify, even without doing the experiment, that the book is going to actually hit the ground first. And the reason for that is we really have all these air particles surrounding us, and this includes the book and the sheet of paper. So when you let go of both of those objects, they fall through the air, and the air is actually going to push back against it. It's going to provide some type of resistance. And as a result, that resistance actually decreases the downward acceleration. It's actually going to make them not speed up as much as if the air wasn't there. That's why we ignore air resistance. Air resistance is tricky. It depends on a couple things. The speed of the object, the surface area that's exposed to the air. There's all sorts of things that we don't really want to consider when we analyze this type of motion. So we simplify it by saying that we're looking at freely falling objects, where there's no air resistance and it's only the influence of gravity. And when that happens, we get this nice acceleration of gravity value of 9.8 meters per second squared in the downward direction. So, with that in mind, you can see here there's this little nice diagram on the right side of the screen. This shows us this idea of air versus no air. The left side image, where it says it's the air-filled tube, you have a rock and a piece of paper. If you put them at the same height and let them drop, what happens is the rock is going to fall first. That air is not affecting the rock's falling motion as much as the piece of paper. On the other hand, if we get all the air out of there, create a vacuum, well, now there's nothing to resist that motion, and everything falls at the same rate. And that rate is, it has an acceleration of 9.8 meters per second squared on Earth at the Earth's surface. So, when we look at problems that have falling motion, we're going to actually do a couple things. First of all, we like to say that the downward direction is negative. Now, you can actually modify this if you want to, but when we do it in class, we are going to have downward be negative, which means upward is going to be positive. So we have a sense of direction there and a sense of displacement, position, so that when we look at what's the displacement of an object, if it's negative, that means it's falling toward the Earth. If it's positive, that means it's moving up away from the Earth. The other thing is, because of that directional sign convention we're going to use, we're going to make the acceleration negative. So now our acceleration is going to be negative 9.8 meters per second squared. And in physics, you'll see that symbolized as a lowercase g, little g, so to speak. And anytime you see that symbol, that means they're using the acceleration of gravity. So what we can do is we can actually rewrite our kinematics equations for falling objects. And you can see them on the bottom of the screen here, that we have those four equations we've been using. Just now, a couple things. First of all the a's are now replaced with g. If it's falling and is in free fall, we can assume that the acceleration is that negative 9.8 meters per second squared. We also have, instead of delta x, which is horizontal. Delta y makes more sense. So really, this is acceleration. It's the same types of problems we've been looking at. Just now, we have an acceleration, 9.8 meters per second squared down, and we're just now dealing with objects that are rising and falling. So that's what we actually want to look at here in the second part of this video. How does the type of motion react to this downward acceleration? So there's three real cases we're going to have. And the first case is, what happens when we release an object at rest? So let's just say we have a ball, we hold it out, it's just in the palm of our hand, or we're holding it above the ground, and we let go. As soon as we let go, we can say at the very beginning, let's just say we start a stopwatch, time is 0, our initial velocity is 0, and our displacement 0. This is at the very beginning. Well, when we let go, it begins to accelerate, and it's accelerating downward at 9.8 meters per second squared. And we can actually use our kinematics equations to figure out all these different things. After 1 second, well, we can use our Vf equals Vi plus g times t, g being the acceleration of gravity. That tells us that after 1 second, its instantaneous velocity is negative 9.8 meters per second. Negative meaning it's falling toward the ground. Similarly, we can use our delta y equals Vit plus 1/2 gt squared to figure out the displacement. I got rid of the Vi times t because our initial velocity was 0, and we find that after 1 second, meaning it's moving downward. I can extend it for another second, and now after 2 seconds, my velocity is 19.6 meters per second squared downward. So again, because our acceleration is 9.8 meters per second squared down, every second its speed will increase 9.8 meters per second, but in the downward direction. So that's why we have that pattern set up. And again, I can find my displacement by using 1/2 gt squared. If I do that, I find that after 2 seconds, it actually fell 19.6 meters from where it began, back at time equals 0. So it's still acceleration. That's the key here. So the situation is, let's say we take that same ball, and instead of just dropping it, we actually throw it downward. Well, now we actually have a negative initial velocity. It's not 0, now it's just some negative value. But we can still apply these same rules. It's still accelerating. In fact, it's accelerating at negative 9.8 meters per second squared. and we can still use those equations to figure out some of this information. So after 1 second, we have our Vf equals Vi plus g times t. I can apply that, and I find after 1 second, it's at negative 19.8 meters per second. So it's moving pretty fast. And in terms of my displacement, again, I can use my delta y equals Vit plus 1/2 gt squared. And when I do that, I find it actually fell 14.9 meters. If I extend it for 2 seconds, I can go through the same process. I find now after 2 seconds, its velocity is negative 29.6 meters per second, negative meaning downward, and my displacement is negative 39.6 meters from the beginning. So all throwing an object downward does to its motion is it just gives it that initial downward velocity, which means it's going to travel farther, and it means its speed is going to be greater at all those points just because of the fact you gave it that initial downward velocity. Now, on to the third type, and this type's the more interesting one in my opinion. What happens if we throw something up in the air? Well, it's technically falling in the sense of there is that downward acceleration, but because we throw it upward, we actually have a starting positive velocity. And because of that, it's going to slow down because, as we mentioned before, if the velocity is in the opposite direction as the acceleration, it slows down. So you can see here at the bottom, at time equals 0, let's just say we throw it up at 19.6 meters per second. Okay, that's our initial velocity. Our delta y is 0 because we're at the beginning. After 1 second, well, I can apply my kinematics equations, and I find that my velocity does in fact decrease. I'm now at positive 9.8 meters per second. I'm still moving upward, or the ball is still moving upward, but it's now a lot less because it's accelerating downward. And my displacement is going to be positive, so it actually goes up in the air 14.7 meters from where I started. And if I let it go 1 more second, well, now all of a sudden, if you notice, my velocity is 0. So there is a moment of time in the air. If you throw something up in the air, it's actually at rest. It's for a very, very small instant of time, but that's the point where it's turning around. The acceleration is pulling it downward. It's accelerating downward, so it's going to slow down on its way up, and then when it reaches that maximum point, it's going to start speeding up in the downward direction. Now, at that peak, it is still accelerating. That is something that a lot of people mistake. Just because it gets to the peak and it has a velocity of 0, that does not mean its acceleration is 0. If that were the case, then it would just hang up in the air, and that would be really weird. So it is still accelerating at all points here, but at the very peak of its motion, the velocity is 0. And you can see there that our displacement is now 19.6 meters. So let's just keep it going. So now after 3 seconds, what happens? Well, we have a velocity of 0 at the top, so now it's going to start getting faster in the downward direction, so it's going to start moving back down. And it turns out, after 3 seconds, our velocity is negative 9.8, and our displacement is 14.7 meters. And if we let it go 1 more second, so at 4 seconds, our velocity, actually I made a mistake there. That should actually be negative 19.6 meters per second, and my displacement should be 0. So what we actually have from this is an interesting pattern. When you throw an object up in the air, the first half of its motion up to the peak is exactly the same as the second half of its motion back down to where it started, just flipped upside down. All the velocities flip. We have at 1 second it's 1 second we have 9.8 meters per second as its velocity. At 3 seconds it's at the same place, but now it's negative 9.8 meters per second. So what we have there is this nice mirror pattern which we can use in problem solving to actually help us solve some problems. So, to kind of wrap up here, we go back to our 2 questions at the beginning. What type of motion does a falling object exhibit? It is accelerated motion. And we talked about the idea of free fall. We said that when it's in free fall, its acceleration, we know, is that little g value of 9.8 meters per second squared downward. We're going to make it negative to indicate that downward motion, and we can use it in any problems we look at. The second thing, how does falling motion apply to a ball thrown into the air or any other type of ball thrown in some way, shape, or form? If you let it go from rest, it just accelerates at negative 9.8 meters per second. If you throw it downward, same thing. It accelerates at negative 9.8 meters per second. If you throw it up in the air, same thing. It's going to accelerate at 9.8 meters per second squared downward. It just, if you throw it up in the air, it's going to slow down first to 0, and then it's going to turn around and start speeding up and drop back down to the ground. We're going to look at this a lot more in class, specifically in terms of problem solving. How do we solve some of these types of problems with rising motion, falling motion, but mainly free fall motion. And it's just applying those acceleration equations we've looked at before, just now vertically with a known acceleration. So, that concludes this video. I will see you in class.